All right, we are going to get started here. If you can hear music in the background, it's because Beauty and the Beast is playing at a random establishment that I'm hanging out at in order to get this video recorded. So, lucky you if you hear the music. We are going to be talking about today distributions and specifically the shape of distributions. So that's what we're going to call this lesson, the shape of distributions. The shape of distributions. And let's get started. There's actually, let's see, how many do we want to go over? We want to go over, I guess, 4, maybe 5 distributions that are kind of the way that data kind of represents itself, the way that it ends up coming out. One of the most common, so let's do this. We're going to say 5 shapes, 5 distribution shapes. All right. And let's talk specifically about my favorite, which is called the bell-shaped distribution. And the reason we call it this is because when you line up the data, let's say we line it up on a dot plot, we've got our tallies here. It doesn't even matter what the scale is. We could count by ones, we could count by fives or tens, but is what ends up happening when you have a bell-shaped distribution is it kind of ends up having data clustered around the center. It doesn't have to be exactly symmetrical, although a lot of times it ends up looking symmetrical. Maybe we have something that looks like this. So it's not exactly symmetrical, but you can see that the data kind of line themselves up nicely around the center, and then less frequent on the kind of ends of whatever the scale is. So this is a really important distribution because many things in the real world take on a bell-shaped distribution. If we're measuring something like height or weight or IQ or test scores, these things tend to line themselves up where most people's kind of values center around the middle, whatever that value is. And then as you move out from the middle, you get less and less people that kind of, are found in those categories. So it ends up kind of being a bell shape. And there's actually a lot that we can do with the bell-shaped distribution because really, you end up getting like 99% of people that kind of fall within, this bell. And then you get these very small amounts of people that end up on the ends of things. And that's very useful. And we're going to talk about that a lot more later on. But the main thing you need to know is that the bell-shaped distribution has most of the data in the middle. This is also a great way to use the mean as the measure of center. So we're saying in a bell-shaped distribution, the mean, the arithmetic mean that we talked about, is a good measure of center, which is great. Because there's not, the extremes tend to cancel themselves out, and so you get to see kind of where most of the data is if you add up all the values and divide by how many there are. The mean is a good measure of center. And it's usually close. The mean is usually approximately equal to the median when you're dealing with bell shape too. Why draw this squiggly equal sign? Because it doesn't have to be exactly equal, but they're close to each other. That doesn't always happen in other types of distributions. We don't always have the mean approximately equal to the median, right? But this is our most, I would say, most common distribution that we end up dealing with. in the real world. Let's talk about the next type. The next type of distribution is something that is called a skewed distribution. Right? Skewed distribution. What does that look like? A skewed distribution, and again, we're kind of giving ourselves, a number line to work with. We're going to mark it off. It doesn't matter what those numbers are, as long as they're even intervals. And then a skewed distribution starts to look like this, where you could either have it look like this, where things are kind of lining themselves up in one direction. It doesn't have to be exactly skewed, but is what ends up happening is you get this bump on one side and kind of a tail on the other. And this can also happen going the other way. So let's take a look at that. I'm going to draw again some more scales. And you can also have a distribution line up. You've got these values kind of on the right, kind of cluster, and then they kind of decrease in frequency as you go to the left. So this is kind of what it looks like. So we have our skew going the other way. This is an important difference between these two. Sometimes you have values that line up in the lower end, where more people are kind of collecting themselves in the lower end, and then in the other case, people are collecting themselves in the higher end. Data is collected in the higher end with a few outliers as you go the other direction. So these have names, and we use the tail to kind of describe the name of the distribution. So in this particular case, it feels like your distribution is skewed to the left because that's where all the data is, but we actually use the tail to describe the distribution. So this is actually skewed. We say it's skewed to the right because that's where the tail is. So it's a lot of times people tend to want to say that it's skewed to the left, but it's actually based on the tail, which means it's skewed right. And then you should be able to kind of infer that this data set is going to be skewed left. So they have names. Okay, this is skewed distribution, skewed to the left. This top one here is skewed to the right. Now, there's some other things that are important to know about skewed distributions. First of all, we don't want to use the mean to measure the center. It's not a good measure of center. The median is much better. So yay for the median. And in this case, the median in this particular case is going to be less than the mean. Because what's going to happen in this skewed right distribution is that most of the values are lining up on one side. And so if you positionally find the middle, it's going to be a lower value because most of the values are low. If you calculate the mean, these higher values are going to kind of increase the mean. They're going to push up the mean a little bit more, and it's going to make it look like everyone has a higher value than they actually do. So the median in the case of a skewed right distribution will always be lower than the mean, and the median is the best way to determine the middle. We're talking about skewed left distribution. You should also be able to infer that in this case, the median, what's going to happen? It's going to be greater than the mean because there's more values positionally in the higher end over here than there are low. But the mean is going to be affected by those low values. It's going to make it look like the overall data has a lower value than it actually than most actually are demonstrating. So we're going to want to use the median again to measure the middle, and it's going to be different than the mean. It's going to be greater in the case of skewed left data. All right, so that is kind of a introduction to skewed distributions. So let's see here. We want to move on to another distribution. Let's take a look. This next one is called a uniform distribution. And this could happen where you get things kind of evenly distributed amongst the data. So the scale. So let's say whatever our scale is, doesn't matter what it is. Most of the time the scale would have numbers, but I don't want to limit us to just putting, 1, 2, 3, 4, and 5 here. I want to kind of illustrate the fact that it doesn't matter what the data values are. If you end up with something where kind of whatever your value is, you end up with the same amount, let's say 2 each time, this is called a uniform distribution. If you think about uniforms, it's something that everyone wears to look the same. So the hint is kind of in the vocabulary that you're talking about a distribution where it's evenly distributed throughout kind of the range of the data. And if you were to draw a histogram of this, it would look like just boxes that are all the same height. It looks something like that. That's a uniform distribution where the data is evenly distributed. Let's do this. The data is evenly distributed through the data set. Or maybe it is equal through possible values. Right? And that doesn't happen as often, but in this particular case, the mean is going to be equal to the median. So they're both pretty good measures of center. And they're going to be the same. All right. Last, this is actually number 4 when it comes to it, but this one is called a bimodal distribution. A bimodal distribution is kind of has, I'm going to draw like a dot plot, basically means that you've got bi, which is 2, and modal, we're talking about the mode, what happens the most. So you're going to get a distribution where, you get maybe 2 different numbers are going to peak. So maybe you have something that looks like this. It doesn't necessarily have to be symmetric, but you have 2 things that kind of stand out like more than others. So if we were to draw a shape around this, it would look like that. We've got these 2 peaks. And they're not always symmetric. The peaks don't always have to be equally spaced from the middle, but they can be symmetric. Either way, you're going to have 2 very common data sets. So this might be, let's say, like you're quizzing a college classroom, and maybe it's like a senior class in college, and you say, "What's your age?" And then all of a sudden, 2 ages come up more than any other ages, and that would be like 20 and 21. And those ages would come up the most, but then you'd have some people who are younger than that, some people that were maybe older than that, but two numbers would pop up, and and so you can have a distribution with um, that's symmetric and bimodal, that's asymmetric and bimodal. So we don't want to make any kind of declarations about the mean and the median. It kind of depends how it's dispersed, but it just has two modes. That's kind of the hallmark of a bimodal distribution. All right. Now, of all these distributions, these four that we've talked about, they can fit into a category of being symmetric or asymmetric. So let's kind of split this up. And this is the last kind of distribution that we're talking about, is symmetric. Symmetric distributions. Now let's think about that. We've just covered four different distributions. One, two, let's do this. I'm going to draw our tiny distributions here. 1, 2, 3, 4. And we're going to kind of ask ourselves, is the distribution symmetric? Well, we talked about the bell-shaped distribution, and we said, yes, it is symmetric. You could kind of draw a line cutting this distribution in half, and it would look the same on both sides. So the answer to this is it symmetric? The answer is yes. The next type of distribution that we had was skewed. And I'll just draw the skewed right distribution. If you draw a line halfway in between the data, does it look the same on both sides? No, then it's not symmetric. How about if we drew a uniform distribution, which again, it would just look like the same all the way across? Of course, this is going to be symmetric. If you draw a line through it, it's going to look the same. And we're going to say yes to this. And then this last one is a bimodal distribution, and it could be symmetric, and it might not be symmetric. So let's see here. If it's symmetric, it might look like something like this. If it's not symmetric, and in that case, we would say yes, it is. But if we were to draw a different kind of example of this, let's put it above here, you could have something that looks like this, right, where it has two modes, and in that case, it would not be symmetric. So this depends. Right? So these are our four types of distributions, and then within the four types, you have to decide, is it symmetric or isn't it? Symmetric distributions, this is an important point to make. Symmetric distributions will have a mean fairly close to the median. So in this case, in this case of this bell-shaped, the mean would be approximately equal to the median. In this case, the mean is not equal to the median. In the uniform, this is a not equal sign. Let's try and clean that up. Right here, we're saying that the mean does not equal the median. In the case of uniform, we're going to say the mean is approximately equal to the median. And then last but not least, in this case of bimodal, it depends. It depends on if it's symmetric or not. If it's symmetric, the mean's going to equal the median approximately. And if it's not symmetric, the mean and the median will be different. All right, so that's kind of an intro into shapes of distributions. Ask questions if you have them, and